So we'll do section 3.4, problem number 12 to practice using the second derivative test. So number 12, it gives us this function f of x equals 5x plus 6x to the negative 1. And it says that this function has one local minimum and one local maximum. And it wants us to say where the local min and where the local min is and where the local max is. And you can do that using the techniques we've already talked about, but you can also do this using the second derivative test. So that's what we're going to do right now, just to practice using the second derivative test. So I wrote the problem down and also the steps for using the second derivative test. So basically, the second derivative test, it says if f has a critical number at x equals c, then la la la, right? So we want to first find the critical numbers. That's your first step, which means we have to find out where f prime of x equals 0 and where f prime of x does not exist. And so let's go ahead and do that. In order to do that, we should find f prime, right? So f prime of x, if f of x is 5x plus 6x to the negative 1, that negative 1's covered up. So f of x is 5x plus 6x to the negative 1. F prime of x is going to be 5 minus 6x to the negative 2. Exponent drops down, so we have negative 1 times 6, which gives us minus 6x, and then negative 1 minus 1 is negative 2. So another way that we can write this is we can write it 5 minus 6 over x squared. And this way it's easier to find out where f prime of x equals 0 and where f prime of x does not exist. So if you have a fraction, which we do in this case, the derivative will not exist when the denominator is 0. So in this case, we would say for the does not exist part, x squared equals 0, which means that x equals 0. And it turns out that x equals 0 is actually not in the domain of our function. So it can't be a maximum or a minimum. What I mean by it's not in the domain is if we go to like the original function, f of x equals 5x plus 6x to the negative 1. Like this can be written as 5x plus 6 over x, because 6x to the negative 1 is same thing as 6 over x to the first power. And if we were to plug in 0 for x, we'd have 5 times 0 plus 6 over 0, and this part is undefined. And so that's why we say that 0 is not in the domain. So it turns out that this 0 that I got down here, that cannot be a maximum or minimum, because it's not even in the domain. Like it's not a number that you can plug into your function and get a real number. So let's focus on the f prime of x equals 0 part. So we'll focus on this part instead. Well, we would focus on it anyway. We want to get all of our critical numbers. So we'll have 5 minus 6 over x squared. Our derivative equals 0. And I guess what I'll do is I'm going to move the 6 over x squared to the other side. One thing you can do right away is multiply both sides by the x squared to get rid of the denominator, but I'm just going to move the 6 over x squared to the other side. I think that'll make it a little bit less messy. So now I'm going to multiply both sides by the denominator, x squared. And I end up with 5x squared equals 6, because these x squares cancel, which is what I wanted. And I'm trying to get x by itself. So now I'll divide both sides by 5. So these cancel, and I get x squared equals 6 over 5. And then last of all, to get x completely by itself, I'll take the square root of both sides. Just make sure you put plus or minus on the right side. And I end up with x equals the square root of plus or minus 6 over 5. So my critical numbers, so notice the first step was to find the critical numbers and yeah, find the critical numbers. So I just found them. So my critical numbers were positive root 6 over 5, negative root 6 over 5. And then we also had that 0, but that 0 wasn't in the domain. So that's not gonna, that we don't really have to deal with that. Because we know it's not a possibility to be a max or a min. And this problem's asking us to find max or min. So we found our critical numbers. This is our first step right here. And so now we'll go ahead and do the second step, which is to plug the critical numbers, those that are actually in the domain of f, into f double prime of x. So whatever you get for your critical numbers, plug them into your second derivative. And that's the process of using the second derivative test. So I want to remind you, this is completely different from the process that I talk about in section 3.3. It's a different technique for finding maxima and minima. So just keep that in mind, that it's different. So if you're going to use this technique, like don't do the stuff that you do with the other technique and vice versa. Like I sometimes see people mixing them up and then ending up in a big mess. So like don't mix them together. I mean, mixing them together, that's what I mean. You know, and then like you're doing one part of one technique and another part of another technique, and then it just all gets messed up. So we're going to go ahead and do the second step for this technique, which is using the second derivative test. So we're going to plug our critical numbers into f double prime of x, which means we have to find f double prime of x, right? So let's see, here's our f prime of x. I'm going to go ahead and bring this down. So here's our f prime of x. So we can find f double prime of x now. F double prime of x is the derivative of this thing. We know the derivative of 5 is just 0, right? And then for the negative 6x to the negative 2, we bring the negative 2 down. So negative 2 times negative 6 is a positive 12. Here, let me write this out just to make sure. So we have minus negative 2 times 6, x to the negative 2 minus 1. Using that, our differentiation rule, that the derivative of x to the n is n times x to the n minus 1. So, and I wanted to write this one out just because like I want you to notice you have a double negative, so that's positive. So we'll have a positive 12 times 6, which is 12. Sorry, 2 times 6, which is 12. I'm like thinking ahead. And then negative 2 minus 1 is negative 3. So we have 12x to the negative 3, or in other words, 12 over x cubed. Using this algebra rule, the a to the negative m is the same thing as 1 over a to the m. So there's our second derivative, and we need to plug in our critical numbers. So, and we're specifically plugging in the root 6 over 5 and the negative root 6 over 5. We don't have to worry about the 0 because the 0, that's not in the domain. Sorry, 0. We're going to ignore you. So we're going to find f double prime of positive root 6 over 5 and f double prime of negative root 6 over 5. Let me make sure once again that okay, yes. So we'll plug these in, and actually we don't really care what the value is. All we really care about is the sign. I just want to know if this is positive or negative. So this, I have 12 over root 6/5 cubed. I know this is positive. So what that means, so according to the second derivative test, is when your second derivative is positive, second derivative at your critical number is positive, then our function has a local minimum. So in this case, we have a local min at x equals root 6 over 5. The idea behind this is that if your function's the second derivative is positive, that means your function is concave up right there, and so you would have a minimum. That's the idea. And then for f double prime of negative 6 over 5, we'll have 12 over negative root 6 over 5 cubed. And I know that if I cube a negative number, I'm going to get a negative. So I know this is negative, which means my function's concave down, which means I'll have a local max there. And again, just going back to the second derivative test, just to reinforce this, when f double prime is less than 0, so when f double prime of your critical number is negative, then your function has a local max there. So we get to say that we have a local min at x equals root 6 over 5 and a local max at negative root 6 over 5. Let's go ahead and enter this. So a maximum was at negative root 6 over 5. And the minimum was at positive root 6 over 5. And so far, so good. Now to get the other half of the point for this problem, it's asking us for the value. And so what we have to do is plug these numbers into the function. So for the value part, this part right here, we're gonna take our negative root 6 over 5 and plug that in for x. And so I'm just going to use a calculator for that. Right, like, right, of course, right. So I'll have f of negative root 6 over 5. I'm going to put this in the calculator. So this is going to be 5 times negative root 6 over 5 plus 6 times negative root 6 over 5. I'm running out of room. Raised to the power of negative 1. Okay, so let's go to the calculator. Hello, beloved calculator. So 5 negative, or you know what, you can just, you can just totally enter it. If you want the exact answer, you can just enter it here, like what I just entered. So let's just do that. So that'll give us the exact value, right? The calculator is just going to give us an estimate, an approximation, but like, so I'm going to enter I'm just going to put in the exact value. So 5 times all of this, I'm just going to copy and paste it. Plus 6 times all of that raised to the power of negative 1. So there we go. That's the exact value. If you want like an approximation, then use the calculator. So for the other one, I'll plug in positive root 6 over 5 for x. And there I will get my exact value. Let's just graph this just so you see it, get a picture of what's going on. And then this will be the last video, I promise, for this section, for section 3.4. So we're gonna graph the function y equals 5x plus 6x to the negative 1. Which is the same thing as 6 over x. And there's our curve. So notice we have a minimum here and a maximum here. We have an asymptote at x equals 0. So notice like the curve doesn't actually touch the y-axis, even though it kind of looks like it does. But there's an asymptote, a vertical asymptote there. And let's see what the square root of 6 over 5, what that was, 1.095. And notice we see that right here as the min. And then if I stick a negative in front of this, notice I get negative 1.095. That's right here. And then if I use the function, I get these other numbers. So like plugging in the positive root 6 over 5, I get that 10.954. And then if I plug in the negative, I get negative 10.954. So there you have it. I hope you're able to do your homework, but if you need help, come to our work session. Take care. Bye.